Muy buenas tardes. Les damos la bienvenida.
Good evening, ladies and gentlemen. Welcome to our lecture, which is the second lecture of the cycle we have developed with the CERN since last year. As you know, you had the privilege of attending the first cycle of lectures. The cycle was part of the anniversary, the 60th anniversary of the CERN. We agreed on having a cycle of conferences in Spain targeting general public. We had the contribution of Professor Bertolucci, then the Director General of CERN gave the closing lecture, and now we are starting with a shorter cycle, 3 years, with a continuity, and we have the pleasure. We have the honor of having with us lady physicist Dr. Gianotti, Director General from January 2016 at CERN. It is a great pleasure to have Dr. Gianotti with us. She will elaborate on CERN and she will present the next step on the CERN Large Hadron Collider. I would like to thank Dr. Jimenez, Director General from the CERN Technology Division. He has been the one making this possible, the first and the second edition of the cycle. I'd like to thank Professor Cayetano Lopez, full professor from the Autonomous University of Madrid, Director General of CIEMAT. And he's going to make an introduction on the lady will be introduced by the Director General. So our friend, as you know, will make this introduction. Professor Lopez will make the introduction. Dr. Gianotti's mandate will begin on the 1st January 2016, and needless to say that Dr. Gianotti is an outstanding expert. We have here the Secretary of State, Research and Development and Innovation. So thank you, and you're welcome. You're at home here. And the floor is to Professor Cayetano Lopez, who will make the introduction. Professor Lopez, you have the floor, sir. Director General of the CIEMAT.
Querida Secretaria de Estado,
Dear Secretary of State,
querida
Research, Development and Innovation, Secretary General on Science and Innovation, Director of the Foundation, BBVA, dear Dr. Fabiola Gianotti, dear friends and colleagues, dear all, I'd like to thank BBVA Foundation. First of all, I'd like to thank the Foundation for organizing the cycle of conferences. This is a very energetic, intelligent policy of helping and backing up sciences and scientific development. We would like to give a token of recognition to the Foundation for this opportunity, and it is a great pleasure for me to introduce Dr. Fabiola Gianotti and CERN. Great pleasure, a privilege to be here. Back in 1967-68, many years ago, when I was about to finish my studies at the Complutense University, at that time was named the University of Madrid, we had a lot of political turmoils and commitment among students in the line of the general climate in Spain and worldwide. In our case, the autochthonous feeling was fighting against Francoism, against dictatorship. And to that movement, we had to add something. There was a motivation, a very special moment for us students in the field of physics. We were protesting against the fact that Spain was about to leave the CERN. We were saying that we should pertain to this international entity, CERN. Even though we might not know at that time what it was the symbol of excellence, in search for excellence and scientific cooperation. At that time, We had lots of demonstrations, and Spain had pertained to CERN since '61, only 7 years after the foundation. But the scientific yield were not many contributions. In experimental physics, we had the CMR, it was the group of energy, nuclear energy, a lab which was able to contribute to the construction and operation of the big infrastructures, part of the core at CERN, as well as contributing to analyzing data obtained at CERN. Let's say that at that time I got in touch with the experimental group of energy, nuclear energy group, and it was Antonio Gillette at that time who was in charge of it, and I decided to become a physicist in the field of experimental physics. Due to the political turmoil, the characteristics at that time, I couldn't become an expert in fundamental particles, and I just became theoretical physicist. And, well, that took place in '69 when I decided to study that, and cooperation with CMAT and other emerging groups, mainly theoretical groups from different universities, kept alive, and we had the presence of Spain at the CERN and the participation at the different studies, PS, SPS, PPVAS, all the parts preparing the experiences to take place at the Large Electron Accelerator, which required a tunnel of 27 kilometers as circumference, and it is where the Large Hadron Collider is now. The Large Hadron Collider. Back in '83, and part of what we did to try to present Spain internationally active with the presence that would correspond to our reality as a country after the transition towards a democratic regime, we became again member of CERN. On this occasion, and at the difference, we re-entered the CERN, but there were measures to strengthen our capacity of research and development, making this productive, measures that had a great importance for the future of high-energy physics in our country. It is true, and I must say, that we didn't reach the objectives, which were a bit too ambitious, what was said at the beginning, but I would like to mention that it was the CMAT where they started working into our getting back into CERN. Juan Antonio Rubio, Director General of the entity, who passed away back in 2010 when he was still a Director General. Then I, in '83, became member of the group, the Council of CERN. It is the maximum entity with representation of member countries, and as a scientific delegate representing Spain at the Council, I stayed there during 10 years, and 32 years ago, because that was '83, but I remember as if it were now, I had to carry, during my first trip to Geneva, I was carrying a check of 11 million Swiss francs, which was a huge amount at that time. And even now, it's a huge amount. And I was worried it was like burning my wallet till I got there. And at that moment, there were two excellent Director Generals I had met there, Dr. Schopper and Dr. Rubia, Carlos Rubia. At that time, it was the Large Electron Collider phase, but they started giving a thought to the Large Hadron Collider and seeing the difficulties of the super collider that was designed by North American experts, which was supposed to be constructed in Texas with within a tunnel 87 kilometers circumference. That was abandoned in '93. Then along the '80s, Spanish groups, we were participating at the different tests And now we have a very relevant contribution in all the detection systems. I knew about it, I had been there, I had been informed about it, many anecdotes. Of course, I'm not going to start mentioning anecdotes now, but my experience as a delegate in the Council made me understand the importance, its symbolic importance, and the scientific importance. CERN started back in the 50s, the beginning of the 50s, prior to the common market, the embryo of the European Union, at a time when Europe was about to reconstruct itself after the Second World War. Those were times where the importance was on top of having ambitious scientific programs, which were not possible separately. We wanted to foster cooperation in the field of sciences. Like in many other cases, there were divisions and other problems during the Second World War. And then nowadays CERN has become the world reference in the field of particle physics, high energy frontiers, where we have scientists and groups of scientists from all over the world. This is a very important example of what we people from Europe we can achieve when we get together, when we work for a common goal. The objective of the CERN is going deeply into knowing the fundamental components of the matter and knowing the laws underlying the behavior. So basic research, and sometimes it is considered as lacking social usefulness. Of course, that is not the main objective of CERN, but answering questions, main questions, out of human curiosity on the nature of the world we're living at. And that is the main goal, main objective, a very legitimate goal that won't require further justification, but as it often and always happen, knowledge, even basic knowledge, will trigger applications. And as we know, perhaps something unforeseen, applications in other fields, but with a lot of social impact. What happened with the World Wide Web, which was created at the lab, and you can not even describe the importance of the internet and development of techniques in order to improve experimental devices and the yield. In the case of Spain, our work with CERN has helped us, and it's still a way to go forward in the field of information technology or in the field of particle acceleration techniques, on top of training scientists and technologists in this ambiance of excellent quality and being skillful people worldwide. Having said that, let's think about the lady who's going to give this lecture, Dr. Fabiola Gianotti, Director General from the 1st of January 2016. She will run for a period of 5 years, and we know, and we will never forget, the historical session 4th of July 2012 at the CERN. I was there. I was from Madrid witnessing the discovery of Higgs boson, this scientist from Italy. Dr. Fabiola Gianotti, on behalf of the Atlas collaboration, presented the conclusion, the existence of a new particle that was a pure hypothesis that was presented more than 50 or 40 years ago, and it was proven and it was presented by Dr. Gianotti as a professor, and I'm still a professor. I must say a word on Higgs boson. I had contributed in a very modest way many years ago. Unfortunately, since the 60s, we've been developing a theory, the standard theory of elementary particles, which is the standard model. It's another name for that. That is a case, and this is not the first one in the history of physics, with the unification, conceptual unification of phenomena and interactions that manifest themselves as different empirically. It describes this theory, interactions, strong interactions, electromagnetic, and the weak interactions, and among the most basic quarks, leptons, bosons W and Z. and it's able to predict the amount of data from decades of fundamental and basic research. It is astonishing, the predictive power of this theory, which is amazing. And there is something. The theory can be normalized, predictions make sense only if the mass of all particles mentioned previously would be zero. That is not the case, which is not the case with the exception of the photon. The introduction in our equations of ordinary terms for the mass will breach energies underlying the theory and renormalizing capacity. But since the 60s, there was a very extravagant way of giving mass to the particles without breaching this property that's very important, valuable property. Introducing a field. Structure is not conventional, and with a mechanism known as Higgs mechanism, will transform the coupling to the particles according to mass terms per particle, and this mechanism preserved the good properties of the theory. It is rather odd, but it's fantastic, and this is why they say that Higgs boson will give mass to elementary particles that in other ways won't have mass within the standard theory context. The field implied the existence of a new particle, Higgs boson, that is special, that is different from other particles, and for more than 40 years has been the object of desire in the case of all physicists in experimental physics, trying to close standard theory, and it was a lack of restlessness in the case of physicists who thought this could cover some other process, unknown processes, and then the difficulties to detect the Higgs boson. It was huge, is huge, it's enormous. That's why there were lots of expectations, and this is why the discovery of this particle in practical fields, and the discoverer got the Nobel Prize and the Prince of Asturias Award. But it was something that revealed us a new field. Seeing the fantastic presentation of this lecturer, who was to me unknown at that time, which was so well known worldwide and for all scientists, and I admire this presentation. And now, when we talk about what the Council decided to appoint Dr. Gianotti, and she will be the first lady Director General of CERN. In more than 60 years, for the first time, the lady Dr. Gianotti will take the lead, which is a process in gender equality, and it makes us think about many things we have missed, many opportunities for not taking into consideration the importance of important contributions like the ladies. It is fundamental what she has described, and it is the level of excellence at CERN. And so it is world-leading research coupled with in-depth knowledge of both CERN and the field of experimental particle physics. That is what led CERN to this outcome. But we need something more. CERN is implying more than 14,000 people's efforts, scientists, engineers, PhD candidates, staff. 11,000 are external users of the facilities coming from all over the world. It is obvious how difficult this is, and the work has a very important component. Teamwork is important, how to work together with different cultures, different ideas, different working habits. So the leadership requires leadership capacities and social capacities and management skills. This is what Fabiola Gianotti has for more than 20 years proven within CERN and worldwide at the head of Atlas project from 2009 till 2013. Prior to the CERN, Dr. Fabiola Gianotti got her PhD at Milan University back in '89, having studied a fantastic training, studying music at Milan Conservatory, and she studied fine arts, and this is the humanistic dimension. And what we always say, always endlessly, at all for that, the science and arts and fine arts and being a humanist, that's part of the same human curiosity, the identity, same objectives, different methods. And that's been prone to debates by those who cannot see farther away and won't understand that this is possible. And becoming part of CERN back in the 90s, Dr. Fabiola Gianotti has developed activities in the field of research and development and construction of detection devices. And also she has developed software and also what is related to data analysis, interpretation of data, and analyzing physical relevant results. And we have to say that Dr. Gianotti has a wide range of activities characterizing experimental particle physics, all the characteristics, and you will excuse me for not giving all the details on the many scientific contributions Dr. Gianotti has made and still makes, and they are extraordinary. And this person will become Director General of the CERN is an exceptional scientist, humanist, and thank you for accepting this extraordinary task as being the director at CERN. And thank you for coming to BBVA Foundation to talk about the Large Hadron Collider that was upgraded to work at 2x as high energy, to unveil what is there and who goes beyond Higgs boson, new discoveries and new possibilities in the hand of good researchers. I wish all the best, good luck, success, all the best in life. And the floor is to you, Doctor, Professor. You have the floor. Thank you for being here.
Good evening. I would like to thank Professor Lopez for this very nice introduction. And I'm very happy and honored and pleased to be here in front of this very prestigious audience with the Secretary of State for Research, the Director of the BBVA Foundation, and many other prestigious guests, many colleagues and friends, and also all of you, ladies and gentlemen. So it's a pleasure and honor for me to talk tonight about CERN, about the Large Hadron Collider, about the discovery of the Higgs boson and beyond that. And I'm particularly happy to do so in this wonderful foundation, which shares a lot of values with what we do at CERN, and we'll come back to this point later on, and to be also in this very nice palace. And also I'm very pleased and honored because the Spanish community, physicists, engineers, technicians, and also many young people have made very strong contributions to CERN activities over the years, and in particular to the Large Hadron Collider, including also the discovery of the Higgs boson. So I will start by saying a few words about CERN, although Professor Lopez already has recalled very well the history of this very peculiar organization. So CERN is the largest laboratory in the world for particle physics, and it's a very special place where over the past 60 years, scientists from all over the world have made fundamental research in particle physics, awarded by discoveries. The Higgs boson is the last one. There were many also before. And Nobel Prizes awarded to people, to several scientists from the laboratory. It's also a place where the scientific goals require the development of front-end, cutting-edge technologies and innovation, which is transferred to society. So perhaps the most famous example is the World Wide Web, which was introduced at CERN to facilitate the interaction among the scientists of the laboratory. And then since then it has changed the way society accesses the information. And later on I will give you some other example. CERN is also a place where we train people, tomorrow's scientists, but also students from high school, and also their teachers. And it's a fantastic place to bring, to attract physicists from all over the world, and so to bring the nations together. At CERN work more than 11,000 scientists of more than 110 nationalities. So just one historical slide. CERN was founded in 1954 by 12 European states. Today counts 21 member states, among which Spain. And the goal of the visionary founders of CERN, politicians and scientists, was twofold. On one hand, to give back prestige to European research after the war. During the war, World War II, the axis of research had moved from Europe to the US, also because of the emigration of the persecution and Jewish persecution, etc. But also, the idea was to create an environment that could foster peace after, the disasters of the war. CERN budget amounts to about 1 billion Swiss franc per year, and I would like to stress that this corresponds to 1 cappuccino per year per European citizen on average. On average, because we all know that the cappuccino is very cheap and very good in southern countries, and then you move northward, and then the cappuccino becomes much more expensive and okay, disgusting. Anyway, so on average is 1 cappuccino per year per European citizen. So this is what we are contributing to CERN. This budget is shared by the member states in proportion to their income. So Spain contributes about 8.5%, and it's used to pay the salaries of the about 2,300 staff, plus the other paid personnel, in part, and in part is used to develop, operate, maintain the infrastructure, so the accelerators that are used by the worldwide community to do experiment and to do research at CERN. And this worldwide community, as I mentioned before, is made of thousands of scientists from different nationalities. You can see it covers South America, China, Australia, Russia, Europe, and Africa, etc. Now, if you think that these scientists are old and boring and old-fashioned, you are wrong. Because if you look at the age distribution of the 11,500 scientists that I showed before, you see that the peak is at 26 years. So most of the CERN population is extremely young. I'm also here, and I will not move from here. I will only stay here. Don't laugh. Now, girls are at the level of 20–25%. At any given moment in time at CERN, there are more than 2,000 PhD students. If you ask yourself, where do they go afterwards? About 50% of them remain in research, university or other laboratories, and about 50% of them go to industry. And they are hired by finance, by communication, electronics, engineering. So CERN is a place also where we form the young generation, regardless of whether or not they continue with science or go elsewhere. Okay, so CERN primary mission is science. What we do at CERN is to study the elementary particles, among which we find the building blocks of matters, electrons and quarks, and they are the forces that control their behavior at the most fundamental level. So everybody knows today that matter is made of atoms. Atoms are made of a central nucleus surrounded by a cloud of electrons. Nuclei are made of protons and neutrons, and protons and neutrons are made of more elementary particles called the quarks, held together by other elementary particles called gluons, like the glue. As far as we know today, electrons and quarks are elementary particles. It means that they cannot be cut into smaller pieces. And they are the fundamental constituent of atoms and therefore matters. So everything, this table, myself, you, this little electronic gadget, everything is made of electrons and quarks. We are an ensemble of electrons and quarks and a lot of empty space. Now, particle physics at the modern accelerator, and the most powerful and the most modern accelerators at the Large Hadron Colliders, allow us to study matter, to scrutinize matter, down to scales of the quarks or even smaller. So down to scale of 1 billionth of a billionth of a meter. So accelerators have to be, considered as giant microscope with very high resolution that instead of studying cells, allow us to study the smallest constituents of matter. At the same time, these studies allow us to get insight about the structure and evolution of the universe. So the very, very small allow us to understand also the very, very big. And the reason is the following. We know today, from cosmology, but also from a huge number of experimental observations, that the universe had origin about 14 billion years ago from a big explosion, the so-called Big Bang. So at the beginning, the universe was very dense and very hot. It exploded, and then with time, it expanded and cooled down. But at the beginning, the universe was made of essentially free elementary particles. With time, these particles started to get together to form first neutrons and protons, and then nuclei, and then the atoms of the lighter elements, and then with time, the macrostructure that we know, star, galaxies, planets, etc. But at the beginning, the universe was just made of elementary particles. So by studying the elementary particles, we can understand the behavior of the universe, what happened in the very early universe. So there are two complementary approaches actually to study the history and evolution of the universe. One is to use big telescopes, and actually in the near future, one of them will be based here in Spain, in the Canary Islands. It's called CTA, Cherenkov Telescope Array. But these telescopes can explore the universe until a time which is 380,000 years after the Big Bang. They cannot go more backward in time, and the reason is that before this age here, the universe was opaque. Photons were trapped inside the universe, inside the matter, and they could not go outside, so they could not reach us. The only way to explore this epoch here, before 380,000 years, is to use accelerators. So these two methods are complementary. They're both important and both necessary to advance our knowledge of the universe. So how do we do in practice? What do we do in practice to study the universe in the early stages and other nice things? So what I'm going to present now is scientifically not rigorous. So I hope it will stay in this small room. Well, there are a few cameras, which, but anyway, because otherwise I'm going to be fired even before starting my new job. So what we do, we accelerate two beams of particles, for instance, two beams of protons, and we made them collide. This is made by using accelerators. Accelerators are an ensemble of electric and magnetic field, which are usually housed in underground tunnels, underground rings. So for instance, this picture shows the underground tunnel hosting the Large Hadron Collider, and these blue tubes are contain superconducting magnets used to operate the Large Hadron Collider. So these two beams are accelerated in the ring incrementally at each turn. At some point reach very high energy, the highest possible energy that the accelerator permits, and then they are smashed. Okay? And so when they smash, it's like when you smash your Ferrari against the Ferrari of your neighbor, the two Ferraris goes into thousands of pieces, so to speak. And so you can see how they're made of. Okay? So we can study the fundamental constituent of matter, the quarks, the gluons that I was mentioning before, understand how fundamental matters behave. So this is the first goal. The second goal is that in the collision, you produce a lot of energy, and energy can transform itself into new particles. And the higher the energy of the collision, the heavier the produced particle can be. And so this is the reason why the Higgs boson has only been discovered at CERN, at the LHC, because previous accelerators did not have enough energy to produce the Higgs boson with high rate and in a considerable amount. Okay? And third goal is related to the universe. The energy of the collisions provided by the Large Hadron Collider corresponds to the temperature that the universe had 1/1,000,000 of a second after the Big Bang. So I told you that the universe started with a big explosion and then it cooled down, okay? 1/1,000,000 of a second after the Big Bang, the temperature had the universe had a temperature which corresponds to the LHC energy. So by producing this temperature and this energy, we can understand what happened in the evolution of the universe at this particular time of its history. Now, to study the products of these collisions in which all these nice things happen, what we do, we surround the collision point of the two colliding beams with big instruments, high-tech instruments called particle detectors made of many layers of different materials, silicon, liquid argon, scintillators, etc. They surround the full solid angle, and their goal is to detect, measure, identify all the particles that have been produced in the collisions, and so give us a kind of picture, like a digital camera, a picture of the collision event. And once we have recorded the collision events, we can analyze the data and interpret what happened in that collision, what kind of phenomena were at play, and etc. Okay, now the most advanced project in accelerator-based particle physics is the Large Hadron Collider, LHC. This is a 27-kilometer ring, 100-meter underground, across the border between Switzerland and France. So here you see an aerial view of the region. These are the Alps here, Lake Geneva here. This is Geneva Airport. And this yellow ring indicates the location of the 27-kilometer ring, which is not visible on the surface. It's 100-meter underground. These little white dots show the border between Switzerland here and France. And so over the past years, we have been accelerating two proton beams in the two opposite directions. And these two proton beams have been colliding at 4 points of the accelerators, where we had excavated 4 big caverns and installed 4 big instrument experiments called ALICE, ATLAS, CMS, and LHCb. Operation of the LHC started in 2010, but it was preceded by almost 25 years of very strong, dedicated, and difficult work of the worldwide community, thousands of physicists and engineers from all over the world. It's a very challenging project. So it started in 2010 and operated until 2013. This was called Run 1, the first operation period, which was concluded with the fantastic discovery of the Higgs boson by the ATLAS and CMS experiment. In 2013 and 14, we have been in shutdown. We have stopped accelerators in order to bring some modifications and repairs to be able, later on, this is now, to operate at higher energy. And this year, in 2015, we have restarted operation with higher energy beams and a factor of 2 more energy, which of course allows us to perform the studies I mentioned before with many more opportunities of discoveries and many more opportunities of advancing knowledge. As I mentioned at the beginning, Spain has made very strong contribution to the 4 experiments and to the accelerator in terms of technology, in terms of industrial contribution, in terms of brains, in terms of people, in terms of young people, although of course also the senior people have been very important in this project. Okay, so a few more details about the technological challenges, starting with the accelerator. The accelerator is at this 27-kilometer ring, and you can see here, okay, and the bones, the core of the accelerator is a set of 1,232 high-technology superconducting magnets, which are used to produce very strong magnetic field and therefore confine the 2 proton beams inside the ring and bring them into collision. Being superconducting, they have to operate at very low temperature. Actually, they operate at 1.9 Kelvin, which corresponds to minus 271 degrees, which makes the LHC the coldest place in the universe. Again, remember I told you at the beginning that the universe had origin from this big explosion and then it cooled down and expanded. So if you ask now, what is the temperature of the universe today? The answer is 3 Kelvin. And the LHC operates at 1.9 Kelvin. So we are actually the coldest place in the universe, and also the coolest place in the universe. In each beam, at any time, when the beams are operating at the highest power, there are something like 200,000 billions of protons circulating in one direction and in the other direction, and they collide in the 4 experiment 40 million times a second. So I told you that these experiments, Atlas, CMS, for instance, the biggest one, are like digital camera who have to take pictures of the collision, but this collision happens 40 million times a second. So this camera has to be very, 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 very fast. And although we don't record all the pictures, just a fraction of them, but nevertheless, this detector have to be extremely fast. Also impressive are the detectors. So this is the Atlas detector. You can see this is a human being. So look at the size, impressive size, that's also the beauty of this detector, to which also Spain has contributed in an important way. So the size is half of the Notre Dame Cathedral, and to remain in Paris, the weight of the other experiment, CMS, is larger than the Tour Eiffel and contains more iron. These detectors are enormous, but at the same time they contain a huge number of sensitive elements to record the passage of the various particles. So they contain 100 million sensitive elements made, for instance, of silicon pixels. And in Atlas, we need something like 3,000 kilometers of cables to bring the signal from the detector to the control room where signals are stored. And in 1 year, every experiment records something like 10 petabytes of data. I think everybody knows what a petabyte is, but if you wanted to write this data on DVDs, you will need a stack of 20 million of DVDs or a pile which is 20 kilometers high. So clearly the question is, why? So why we are doing all this, these technological efforts and this, so many physicists and scientists and engineers from all over the world working on this project? What are the goals of this project? Well, the goals are address some open question in fundamental physics that are with us. Some of them now have been solved, some others remain, and to advance fundamental knowledge. So the LHC has been built and conceived and built in order to understand, for instance, what is the origin of the masses of the elementary particles, for instance, the quarks and the electrons that I mentioned before, and this is related to the Higgs boson. And so this question has been, in large part, ticked off. I say in large part because, for the expert in the audience, the masses of quark electrons still contains a little part of mystery. But there are many others. We know today that 95% of the universe is dark. It's called the dark universe, meaning that what we know is only 5% of it. I will come back to this point later, explain a little bit more what it means. We know that the universe is made mostly of matter with very little antimatter. There is nothing wrong nor dangerous with antimatter. The matter is behaving very well as matter, but there is very little antimatter, and we don't know why. We don't know why. What happened at some point of the universe evolution, there has been an imbalance between matter and antimatter, and so matter prevailed, etc., etc. I will try to explain to you in just one slide, and in a very simple way, what Professor Lopez has explained in a more rigorous way scientifically, but I will try to explain in a very, very simple way what is the Higgs boson and why it is so important. So before the discovery of the Higgs boson at the LHC in 2012, we didn't know how the elementary particles acquire a mass. And we didn't know, for instance, why the photon, which you all know, this room is full of photons, is a particle that constitutes the light, is massless, it's just pure energy. Whereas another very important particle, perhaps less familiar to you, called the W boson, which is responsible for radioactive decays, which is responsible for thermonuclear reaction in the sun, which produce the heat that we all receive and allow our life. So why the W boson is a massive particle. It has a mass which corresponds more or less to 100 times the mass of the proton. And this is because in the Standard Model, the theory that describes the elementary particle and their interaction, originally all particles are massless. But this contradicts clearly evidence. And so in 1964, some scientists, among which Robert Brout, François Englert, and Peter Higgs, introduced a mechanism in the theory which would allow elementary particles, some elementary particles to acquire a mass, and other particles to remain massless. And so this mechanism, which is called Brout-Higgs-Englert mechanism, goes essentially like that. At the beginning of everything, at the beginning of the universe, say, of the Big Bang, before that we cannot go, we don't know what happened before, but when the universe started with this Big Bang, all particles were massless, like the photon, and they were running in the universe happily at the speed of light. With time, the temperature goes down, and at some point, and this point is 10 to the minus 11 seconds after the Big Bang, so 100th of a billionth of a second after the Big Bang, the universe reaches a temperature, okay, it was cooling down, reaches a temperature at which the Higgs field comes into play. You can imagine the Higgs field as a medium that starts to permeate the universe. So before that moment, particles were going around in the empty space, but at some point, they see that the universe is permeated by some material, okay? And then they feel that there is something. And imagine this material is, kind of glue or sticky thing. And imagine the elementary particles are little balls. So they go through this medium, but they feel some resistance, so they are slowed down, and also they start to stick the glue and the marmalade and the melassa, is this sticky medium, and they become fatter, and they acquire a mass. So this is the Higgs mechanism by which the elementary particle interacting with this Higgs field that started to permeate the universe at some point of its history, interacting with this medium, acquire a mass. The mechanism theoretically worked well, and it was at least the main solution to the problem of masses. But the problem was that, as a consequence of this mechanism, the theory predicted an additional particle, the famous Higgs boson, and since 1964, this particle has been hunted at all accelerators and laboratories all over the world until it was discovered at CERN in 2012. And this, of course, as you know, gave the Nobel Prize to François Englert and Peter Higgs. Unfortunately, Robert Brout passed away in 2011 before the discovery. Okay. So I'm sure I can anticipate your question. And the question is, who cares? Who cares of the Higgs mechanism, this medium, the Higgs field, and the particles? Who cares about the particle masses? Well, we should care, because if particles are not a mass, in particular, if the fundamental constituent of atoms, so electrons and quarks, are not a mass, atoms will not stick together. And if atoms do not stick together, there is no ordinary matter. There is no you, there is no me, there is nobody. There will be no universe as we know it today. Perhaps there will be a different universe, but we will not be here, and the universe will not be what it is. So we are what we are only because the elementary particles have some specific masses. And until some time ago, we did not know how and how this could be possible. Another thing that I would like to mention is that since 10 to the minus 11 seconds after the Big Bang, since this time, the universe is permeated by the so-called Higgs field, and is still now permeated by the Higgs field. There is a Higgs field in this room. If there was no field, the electrons and quarks in your atoms will not have a mass, because the mass comes from the interaction with the field, and so we will not be here. So also the space is not empty. There's always something permeating the space. Okay, so you could ask, okay, but how did you observe the Higgs boson? How does it look like? Okay, so this is a picture showing the collision of two protons beams at the LHC in the CMS detector. So you see here the yellow arrows indicate the two beams which collide in the middle of the CMS detector. The collision produces many, many tracks, but you can also see these big green towers, which, and these two green towers are the energy deposited in the CMS detector by two photons. The Higgs boson, once produced, disintegrates itself in other particles, and it can disintegrate into two photons. And so the decay of the disintegration of a Higgs boson will look very much like this event here. So what the Atlas and CMS experiments have done, they've analyzed all their data containing photons and two photons, and then they look at the spectrum, and if there is nothing, you just see a falling spectrum like noise. But then if there is a particle with a given mass that decays to two photons, you will see it as a bump, as a peak on the spectrum. And so this is the signal of the Higgs boson. It was not easy to find it, because one detectable Higgs boson is produced every 10,000 billions of every 1,000 billions of proton-proton collisions. So it's like looking not for a needle in a haystack, but a needle in many haystacks, and it required a lot of very clever work, a lot of ingenuity in the analysis to extract this tiny signal of the Higgs boson from the huge amount of collision that we have recorded, and most of this work actually has been done by the young people. Okay, so a little word about now the more recent, because this is past history. So the present and the future. In June 2015, the LHC started operating again after 2 years of shutdown, and produced first collisions at an energy which is a factor of 2 larger than what we have been operating at in the previous year. And this collision were successful, and since then we are operating in this new energy regime. So what are we going to do with this new energy? Well, we are going to address the questions that I mentioned before. You remember the list of questions, only the first one has been ticked off, at least in large part. Another important question is the question related to dark matter. So I mentioned to you the problem of the dark universe. This means that when we look at the night sky in the evening, so we see stars, planets, galaxies, beautiful sky, what we see by eye or with telescopes is only 5% of the universe. Okay? Meaning that only 5% of the universe is made of ordinary matter, the same matter of which we are made. The rest is a question mark. We call it dark universe because dark indicates our ignorance. It's made of some form of matter and energy that we don't know. But also it's called dark because this matter and energy do not interact with our instruments, so we don't see them. And we infer their existence, for instance, the existence of dark matter, by studying the gravitational motion of galaxies, which indicate that there is much more matter out there than what we see. Okay? So today, based on many beautiful experimental observations and measurements, we know that 5% of the universe is what we see, the known matter, like us, made with the same kind of matter, atoms, molecules. 25% is made of an unknown form of matter, called dark matter. And another 70% is made of an even more mysterious form of energy, called dark energy. We have no clue of what dark energy is, frankly speaking. So, in spite of the huge progress that we have made, there are still very intriguing questions to address. So one interesting possibility is that the particle responsible of dark matter could be produced at the LHC in this phase at higher energy from the collision of the proton beams. We don't know if it's going to happen or not, depends on what really dark matter is made of. It's in the hands of nature, but if dark matter is made of kind of particles called supersymmetric particles, I will not go into details, they will be abundantly produced at the LHC, and so it will be really a triumph for science if an underground accelerator at the border between Switzerland and France, one can produce the particle that explain 25% of the universe. And our knowledge of the universe would improve from 5% today to 5% plus 25%, which is 30%. Okay. So one question that people often ask me, will the Higgs boson or other discoveries that you do at the LHC change our life? And my answer to this question is yes, and it did already. And the reason is the following, that in order to discover the Higgs boson, we had to develop high-tech instruments in a huge number of fields. Because particle physics requires really cutting-edge technology developed at CERN and in the collaborating institutes and countries, particularly in Spain. So these technologies developed at CERN found application in a huge number of domains, in particular in the medical domains, medical imaging, cancer therapy, etc. And I would like to mention one example. Today on Earth, there are about 30,000 accelerators built by mankind. Only a handful of them are used, well, not a handful, but a few dozens of them are used in fundamental research at CERN and in many other laboratories. Most of them are used for practical application. Actually, more than half of them are used for medical application. One example is the so-called Hadron therapy, where you bombard the tumor tissue not with rays, but with protons. And protons beams are much more focalized, and so they just penetrate and attack, bombard the tumor tissue and do not expand in the surrounding healthy tissue. Okay, so Hadron therapy today is quite developed, and I think also in Spain there are some ideas perhaps to build one of these centers here, and there are 14 facilities in total in Europe. So this is one example of application in medicine, but there are many other examples. And every time, for instance, you pass through the security in an airport, remember that you are going through a little piece of CERN technology developed initially at CERN. So one slide to stress the important contribution of Spain to CERN in technology, in high-tech items. Some of them are mentioned here. And here you can see the CERN beamline, which is going to be upgraded in the future to operate the LHC at more intensity and more power. And you can see a beautiful snapshot of the world, the little flag indicating the various magnets to which the various countries contributed. And of course, you can see here also the Spanish flag. However, regardless of the applications that our discipline, of course, has and spin-off that it has on society, I would like to mention that fundamental research is the one that mostly stimulates ideas and creativity, because fundamental research is not driven by the final product. When you do applied research in industry, for instance, you have to produce some product, and industry has, of course, some goals of benefits, of return, of time scale, etc. Whereas fundamental research is free. So the fundamental research is where men and women exercise their ideas, their creativity, blue sky innovation, etc. Because there are no constraints. And ideas and creativity are the fuel of progress. And without ideas and creativities, without breakthrough, without big changes in our understanding of the fundamental principle of nature, sooner or later the progress stops. One good example comes from history, and is quantum mechanics, which was developed and was understood mathematically at the beginning of the last century. Now, there is nothing which is so far away from reality, more far away than quantum mechanics, because quantum mechanics has to do with the microscopic world. We live in a macroscopic world, and so, how the microscopic world works has nothing to do with us. And there are some principles of quantum mechanics that are totally abstract and even counterintuitive. Okay? And without quantum mechanics, today we could not exist. There would be no transistor, so we will not be here with this nice webcast, etc. But quantum mechanics was a strong breakthrough. It was not just the evolution of something. The other example I like to give is the light, the electrical light that we. Is not by, the light that we have in this room is not just the evolution of the candle. It's not that by building bigger and bigger candles and more beautiful and more colorful, you get this light. the light we have in this room has required a breakthrough in fundamental knowledge. So without fundamental knowledge, progress does not continue for some time, but then at some point it saturates, and we don't move on. But I would also like to revindicate, in some sense, the importance of knowledge as the importance of arcs per se, regardless of progress, application, and evolution, etc., because knowledge, together with art, is perhaps the highest expression of human beings as clever beings. So it justifies itself by its intrinsic value. We are clever beings, which distinguish us from animals, although sometimes you ask yourself if animals are more clever than a human being, but okay, fine. Our brain is our wealth is fundamental, and not funding art, not funding fundamental knowledge is essentially betraying the essence of human being. And I think these are values that are very much shared with the BBVA Foundation, which I admire very much because it's really targeting fundamental research, basic research, the arts, which are really the most precious values that mankind has. I would like to quote a very nice quote by Bob Wilson. Bob Wilson is the founder of the Fermi National Accelerator Laboratory. This is the second biggest particle accelerator laboratory in the world. It's located in Illinois, near Chicago. So one day, this was in the 70s, a delegation from US Congress visit Fermilab. So they show them around, a very nice facility, blah, blah, blah. And at the end, one of the congressmen asked, okay, yes, this is very interesting, but what will your lab contribute to the defense of the US? And the answer of Mr. Wilson was nothing, but it will make it worth defending. So this is really the importance of what we do. So in conclusion, at CERN, and in particular with the Large Hadron Collider, we are seeking answers to fundamental questions related to the elementary particles and the structure and evolution of the universe. And with the Large Hadron Collider, exploring a new energy frontier, of course, a very important jump has been made in this respect. The discovery of Higgs boson is clearly a step forward in our fundamental knowledge of nature. At the same time, we advance the frontiers of technology, also to the benefit of society, and we train the young people. Another important thing I mentioned at the beginning is the peaceful collaboration, but even more than that, we promote diversity. We promote diversity in all sense. At CERN, people from all over the world, not only different gender, age, ethnicity, work together, and diversity is a strength of mankind. Should not be an obstacle. Sometimes we fight diversity, but diversity is really a strength, is an asset for a richer and more stimulating environment, is an asset also for a better world. Thank you.